talk about these main points. Okay, so we'll touch on seven basic areas. These are all very key areas with respect to the electric grid today. First is some concepts, and one of the biggest challenges, but it's very, very important to us, is bringing together within an organization the operations side and the information technology side. The OT, operations technology, and IT, information technology. So we say the integration of electrical and information infrastructures. Okay, that's very important. We have a lot of valuable data on the operations side that we need to extract, bring across the firewalls into the IT side, the corporate network, so that data can be shared with many other people in the organization. Okay, and we want to deliver meaningful, measurable, and sustainable benefits to the utility, the consumer, the economy, and the environment. And there's much more focus today on the distribution part of the electric grid. Okay, so adding intelligence to the electric grid is not new. For instance, in my career of 48 years, I've been adding intelligence to grid with 6 different companies that I worked for in 48 years. What's new though is what I've shaded in light green. And I call the new stuff, what we call smart grid additions in light green, the smarter grid. Okay? And you can see at the bottom here, for instance, voltage control is shaded halfway. That means that we've been doing voltage control for a long time because voltage is directly proportional to load. Okay? When we lower those secondary voltage, we lower the load. So it's a very good way to manage load and to avoid exceeding a previous peak, especially on a hot summer day. Okay? But we always did that separate from reactive power control or VAR control. We would reduce losses on the grid by doing VAR control. We did that separate, called it power factor control. The light green part of this is today we're doing integrated volt VAR control. We've integrated those two functions together. Okay. We're also integrating a lot of renewable generation at the transmission level, the distribution level, and the end use customer level. In the middle here, sensors is shaded halfway. We're adding a lot of new sensors on the grid. We have a lot of specialized sensors. We've been adding sensors for a long time, but today we have a lot of new specialized sensors. For instance, this one I'm showing in the middle here, I take the oil from the main tank of the transformer and I bring that oil through the sensor, and it can detect up to 9 different gases dissolved in that oil. We call that dissolved gas analysis, or DGA. And the presence of a particular gas is a specific failure mode that's occurring in the transformer. Okay? And the idea is that we want to detect that right away and prevent a big failure, prevent a catastrophic failure of the piece of equipment. Okay? And then we're doing a lot with the distribution management. That's a separate control system to manage the distribution part of the grid. Distribution automation is the intelligence on the feeders downstream of the substation. And then we're adding a lot of smart meters. All right, so there's a lot of smart grid additions being done. But the concept today, the important concept, is a holistic solution. 2 very key words. Holistic means company-wide. It means not for each individual group in the organization, but for the company, for enterprise-wide. So we break the silos down between the groups and bring the groups together. A solution is a set of technology components, typically from different vendors, integrated together to successfully interoperate to meet the business needs of the customer. Okay, so I want to show you 6 solutions, holistic solutions, and these have very strong business cases for electric utilities. The first is asset optimization. And here we're using those specialized sensors and new analytics to determine the health of the asset, both transformers and circuit breakers. Okay, so what's important here is we've moved from reactive maintenance to proactive maintenance. Instead of waiting until something failed and then reacting, we want to prevent the failure. So we're proactive today. What information can we get from the asset? What analytics do we need? And how can we predict the failure modes and stop or prevent a failure from occurring? Second is demand optimization. We're aggregating load and using that as a dispatch tool in the control center. Third is smart metering and two-way communications. Fourth is distribution optimization. This has the strongest business case today and the most focus, optimizing the distribution part of the grid. I'm going to spend a lot more time on that. Fifth is transmission optimization. It's the transmission part of the grid. And what's important here is the use of synchrophasers. You know, we have synchrophaser capability within relays today that can sample a point maybe 50 times per second, where the typical data we use is every 2 to 4 seconds. Okay, so it gives us a lot more insight into what's happening on the grid. And then lastly is workforce and engineering design optimization. You know, in many parts of the world, not only do we have an aging infrastructure, but we have an aging workforce. For instance, in the United States here, within the next 5 years, 40% of the employees and 60% of the executives will retire in the energy industry. So there's a really good opportunities around the world for college graduates in the energy field. Okay, but the other thing is we need to capture the experience of these senior workers before they retire. What you learn at the university is the science of engineering. That's pretty easy to do. Anybody can do that. It's textbooks, courses, professors. But the value you bring to a company when you start working full time after you graduate, it's not what you learned in school, but it's not the science of engineering, it's the art of engineering. How do you apply that science in the real world? And you can't learn that quickly. You have to spend years with experienced people, working with them, you know, going out to the field, seeing the substation, seeing the control center, and working with experienced people, learning from them. That's why all students, all young professionals should have at least one mentor, an experienced person, and spend as much time as you can with that person to learn from them. Mentoring is extremely important. Okay, so if we take these 6 holistic solutions, this is the technology roadmap for them. Okay, and if we just look at the light blue, that's the distribution holistic solution. These 4 boxes in the upper left are software applications. Then we have systems. This is the upper left. Here's the office or control center. Lower left is substation. And lower middle is equipment on the distribution feeders downstream of the substation. So all these blue boxes could be from different vendors, but they all have to successfully talk to each other and exchange information. So that means that they must comply to the same industry standard or standards for successful interoperability. Okay, and then these are some other examples of how important integration is. You know, there's 5 key components that must be invested in. We look at the top here: smart meters, the metering communications, which is automated metering infrastructure, or AMI, the geographic information system, the outage management system, and the distribution management system. Okay. So for instance, with smart meters, in addition to the meter readings that we get, we also can ping certain smart meters and get the voltage at that point on the system. Okay. Um, the geographic information system is the reference system for the network model, for the outage management system, and the distribution management system. Okay. Um, Now, the challenge we have though with distributed generation is that we designed the distribution part of the grid. If you look at the very bottom of the slide here, the distribution controls and protection were traditionally, they were designed to take advantage of electricity flowing in one direction only, from source to load, okay? And when we integrate distributed generation at the end user level, at the distribution level, at the transmission level, we now have electricity flowing in two directions. We have a source side component and a load side component, okay? And this gives us a lot of challenges. For example, our protection ratings with our protective relays, our equipment, may not match the fault currents. Because when we do a protection study, we model the grid and we do a short circuit study because we need to estimate what's the magnitude of the fault current. If there is a fault, what's the magnitude of the current we can expect? And we need to make sure we set the protective relays appropriately, right? When we do that short circuit study, we only look at the source side contribution to the fault. We don't consider a load side contribution. And as the penetration of distributed generation grows, the load side contribution could be significant. But what's more challenging is there's varying fault currents due to the distributed generation because the sun isn't shining all the time and the wind isn't blowing all the time, right? So that makes it even more challenging. Now, this is an example of a microgrid that's operating in Canada. And this village, these people, do not live near any electric utility, okay? So they have their own hydrogen fuel cells, their own solar generation, their own hydro generation, and their base generation is diesel generation. So what we want to do is minimize the use of the diesel because it pollutes the atmosphere and it's very expensive to get diesel fuel to a remote site. Also, we want to maximize the use of the other resources, okay? So in the upper left here, we took a microprocessor-based relay and we added logic to it to be the microgrid controller, okay? And these blue boxes everywhere are high-speed communications boxes. So we know exactly what's happening at least every 2 seconds, okay? And this has been operating, it's called Bella Coola. It's been operating for 12 years now in Canada. So one challenge here is the impact of high penetration of rooftop solar photovoltaic generation on the distribution part of the system. This is a real example from San Diego Gas and Electric. And I wrote this article in Power Electronics Magazine, August 22nd of 2013. And you can find this article online if you search for Power Electronics Magazine and my name, John McDonald. Okay. What the situation is a distribution feeder that brings electricity to very expensive homes along the ocean, the Pacific Ocean. And as you know, in a substation, there's an online tap changer. And the objective of that tap changer is to keep the secondary voltage constant as the primary voltage fluctuates. And it does that by changing taps. But it's a mechanical control device. So the more it operates, it lessens its lifetime. It will have to be replaced, okay? But this has 16 raised positions. and 16 lower positions and a neutral position. So, you know, in a steady state situation, it's not going to be changing taps much, right? Because the voltage is pretty constant. But on this feeder, very quickly, over 35% of the homeowners installed rooftop solar panels. Think about this now. Because of the moisture in the ocean, there's a marine layer of fog over these homes in the morning, blocking the sun's rays. And as that fog burns off, all of a sudden all these homes begin generating at the same time. And the voltage on this feeder actually spikes, right? As soon as that sun sees the photovoltaic panels on that many homes, and they all begin generating, the voltage shoots up like a rocket. It spikes, and then it oscillates over a wide range as the sun goes in and out of the clouds, the fog. This tap changer is trying to keep the secondary voltage constant. Originally, it was operating 5 times per day. It's now operating over 150 times per day. And the lifetime went from 35 years to less than 2 years. It will have to be replaced. So my point here, a couple things. One would be that there's new applications of power electronics in power systems. And what I'm encouraging is the power electronic graduate students and professors work more closely with the power systems graduate students and professors. You know, in IEEE, we have 2 different societies. We have the Power and Energy Society, PES, and we have the Power Electronics Society, PELS, okay? And secondly is, as the penetration of distributed generation increases, the volatility of voltage and reactive power will dramatically change on the grid. We cannot use mechanical controllers anymore. They'll have to be replaced very quickly because the volatility is so great that the frequency of operation increases exponentially. Okay, so that's why we need new applications of power electronics, and that's what I wrote about in this article. I also included at the beginning of the article the voltage waveforms on the feeder, and you'll see the volatility in the waveform. Okay. The goal of organizations today is a digitized grid, but you know, how do you do that? How do you accomplish that? No organization can reach their goal in one step. They don't have enough money, and they don't have enough people and skill sets. So what we do is we help organizations put a roadmap together. And the question is, what is your starting point? You know, what are you doing today? And let's take an example here where a utility has a manually operated network today and a static view of the network configuration. So what is the next step? You know, what can they do? What can they afford to do with money? What can they afford to do with skill sets and people? But we want to make sure that whatever they do has significant benefits back to the organization. So let's add remote control and monitoring, or what we call SCADA, supervisory control and data acquisition. Customer status with trouble calls and smart meters and circuit reclosers. And this will bring increased benefits, 28% lower customer minutes interrupted than the base level. Okay. Next step would be automation and visualization. We had distribution automation, but with power flow analysis, network visualization, and outage management prediction analysis, and this brings 43% lower customer minutes interrupted than the base level. And then we get to be fully digitally enabled, and the benefits here are much greater than 50% better than the base level. And this is with network optimization utilization, asset performance management, and distribution automation. Okay? So Another example here is a utility with 856 distribution feeders or circuits, and they wanted to improve the reliability of their distribution system. Um, well, automating that many circuits is very, very expensive. But the thing is, you don't have to do that. Let's study those circuits. And we find that 200 circuits, or only 23% of the circuits, account for 71% of the total outage minutes. Very important to know this, right? So if we automate only 23% of the circuits, we're accounting for almost 3/4 of all the outage minutes. Okay, much better use of money, right? Much better use of budget money, getting a bigger return on the investment. Okay, but when we do automation, we have to realize that there's two types of data. And for many, many years, we only focused on one type of data, and it was this, the operational data, because that's the data that the operators need in the control center. This is where the SCADA system is located. Has people there 24 hours a day, 7 days a week, monitoring and controlling the grid. And the operational data is the real-time status, performance, and loading of the power system equipment. And it really is the fundamental information used by system operators. And this is points of data. Could be analog points like amps, volts, watts, and VARs, or it could be status points like open, closed, like with a circuit breaker, okay? Or alarms, on, off, you know? The new type of data that we saw in the microprocessor-based devices we started to see for the first time in the 1980s is called non-operational data. And I wrote an article that introduced these concepts to the industry in 2003 in an article, a guest editorial in IEEE Power and Energy magazine. The non-operational data is both points and files. The primary user is typically someone other than the system operator. This could be maintenance information, like dissolved gas, moisture content in oil. It could be a digitized waveform from a relay, like what would be needed by a protection engineer. Okay, so if we compare these two, the operational data is individual time sequence points. Non-op is points or data file. The operational is real-time or near real-time, but the non-operational data is historical, mostly trends over time. The operational, we communicate using standard non-proprietary communication protocols. The non-operational data, the data files, we may need a device vendor's specific format to extract it, but these are all easily supported today. Okay. So we're in the middle now of the next productivity revolution, which we call the Internet of Things. And what we're doing is we're connecting, and by connecting, I mean a big use of communications, okay? Communications is the enabling technology that allows us to automate. So I learned when I was at the university, at Purdue University, with my bachelor's and master's in electrical engineering, but a specialty in power, is I learned that to do power engineering and power system automation, you really need a good knowledge of communications. As I said, communications is the enabling technology that allows us to automate, okay? So what we're doing with the Internet of Things is we're connecting intelligent machines with big data and analytics and with people at work, connecting people any place, any way, anytime for intelligent operation, okay? And I said it earlier that we want holistic solutions. And holistic means enterprise-wide. Break the silos down, not for an individual group. So on the left here, is very typical. Each group in the organization has its own systems, its own intelligent electronic devices, or IEDs, and its own repositories, and it's siloed. There's typically no sharing among the groups. And the goal is, on the right here, is adding a federated data mart. And we break the silos down, and we bring together all the data sources in the enterprise. These are the systems, the microprocessor-based devices, the repositories. Bring these all together. And what we want to do is we want to make sure that all the operational users, these are the operators in the control center, and the non-operational users, and there could be as many as 25 to 30 different groups in the utility that have a need for more data. Okay? And we want to make sure that all of these users have the data that they need. The advantage is on the left here, lower left, we have standard architectures in the substation. We're showing a master data concentrator, slave data concentrators talking downstream to a lot of the microprocessor-based devices, or what we call intelligent electronic devices, IEDs. On the right here, in light blue or cyan, we have a list of all the data sources in the utility, the systems, the devices, the repositories. And on the right, in green, is all the different user groups, all the stakeholder groups. Okay? Things like asset management, power quality, maintenance. Okay? Very important. And what we want is we want all the users to have all the data that they need from all the data sources in the enterprise. So this is the goal, and this is the journey. This is what's exciting today is, for years, it's hard to believe, but in the industry, all of us were reactive. We waited for a call from a customer. We waited for a piece of equipment to explode, okay? And then we reacted. But, by then it was too late. The outage had occurred, or the equipment had already exploded in the substation and destroyed the whole substation, right? Doesn't make a lot of sense to be reactive. Let's prevent the explosion from occurring. Let's prevent the outage from occurring. So we moved to responsive, and we had better situational awareness, better fault location with automated restoration, better crew productivity. But today we've moved up to predictive. We're about halfway up the journey. The question is, what health information do we need from the asset? And then what analytics do we need to analyze that health information to predict a failure mode that may be occurring in the asset? Okay, but that's not enough. We can do a better job with more artificial intelligence, more machine learning, and more use of the digital twin, which is the way we simulate assets. And the digital twin is a good bringing together, combining the physics of the asset with real-time data from the field. But after predictive, we can be prescriptive and eventually autonomous. That's the goal, autonomous. Self-healing, self-provisioning, and extensive autonomous operations with limited human intervention. Okay? But as I said, to do that, we need industry standards. These technology components that are integrated together to form a holistic solution have to interoperate, and they have to comply with the same standard or sets of standards. So on the left here is the Smart Grid Conceptual Reference Model. This is an industry standard. It's 7 domains and how those domains interact with each other. Okay? But the real challenge for us in the industry was IEEE. You can read on the left here, IEEE had identified over 100 standards involved in smart grid, And the IEC had identified over 100 standards involved in smart grid. So IEEE 100 standards, IEC 100 of their standards. And what we did was I was chairman of a board for NIST, the National Institute of Standards and Technology. And we knew that we had to narrow that list down to a smaller, more manageable group of standards. So we narrowed it down, we reduced it down to 16 foundational standards for smart grid. And that's what I'm showing here. This is widely used in the world, and this makes it much easier for everybody, you know, whether you're a vendor, whether you're a user at a utility, whether you're a researcher at a university. It's much easier now to say, you know, what standard or standards impact what the work that I'm doing. Okay. And so it's much easier. There's really only 16 you need to consider. All right. And what's made it even easier is the convergence worldwide of the acceptance of global standards. For instance, from control center to control center, there's one standard in the world called ICCP, Inter-Control Center Communications Protocol, widely used in the world. Second would be control center to field equipment. Here we have the one that we've talked about is, you know, there's two standards. In North America, we use a lot of DNP3, which is Distributed Network Protocol 3. It's also known as IEEE Standard 1815. But European suppliers continue to use IEC 870-5, 101 for serial communications, and 104 for network communications. So there's three levels here: control center to control center, control center to field, and now when we're within the field, the global standard is IEC 61850. But in North America here, we still use a lot of DNP3 for substation and feeder device automation. Okay, so let me finish that.
So thank you very much for being with us, and please accept the e-token of appreciation from on the behalf of the Albag Education Institute, Agra. Thank you very much.
Well, thank you, Rajiv.